everyone. In this video, we will understand what is meant by a power factor, the criteria of improving or correcting a power factor, and we will also understand more about the relation between power factor and types of loads and power. First, let's define a power factor. Well, power factor is the cosine of angle between current and voltage. It can also be defined as the ratio between actual, active or real power to the apparent power. These two definitions can be also expressed as these two formulas. Power factor equals the actual power in kilowatts divided by the apparent power in kilovolt amps. Also, power factor equals cosine theta or cosine the angle between current and voltage. We have mentioned now apparent and active power when defining a power factor, which means that there is a bond or a relation between types of power and the power factor. So let's define types of power. First type is the active power, which is also known as the real power or actual power. It is the rate of producing and transferring electrical energy. It is measured in watts or kilowatts, or also can be measured in megawatts. Simply, we can conclude that it is the productive type of power. Second type of power is the reactive power, which is defined as the power that occurs in AC circuits when the voltage and current are not in phase. It is often expressed or measured in kVAR, which is the kilovolt ampere reactive. We can also conclude that this type of power is not the productive type, and we will understand why this power is not productive shortly. Third type is the apparent power, which also could be defined as the product of voltage in volts and the current. It comprises both active and reactive power. Simply, it is the combination of reactive power and the active power. Now let's indulge into more explanation about types of power and the relation between each. I think many of us are familiar with this triangle, or what is known as the power triangle. In simple words, the main idea of this triangle is that whenever the angle here increases, then the reactive power will increase as well. And this means that this angle is the power factor or the cosine theta. So when cosine theta increases, it means that reactive power also increases and active power decreases. So let's say that this angle, for example, is 0, then cosine 0 equals 1. This means that power factor equals 1. This means that there is no reactive power at all, and all the power is expressed as an active power. What if the angle is, for example, 45? This means that cosine 45 is going to equal 0.7, and 0.7 means that the power factor equals also 0.7, and there will be a reactive power. So when we say that we want to correct a power factor, we actually mean to decrease this angle as much as possible to approach the zero angle, which means also a unity power factor and a less amount of reactive power or the wasted power. Now let's understand why we called reactive power as a non-productive or wasted power. Well, the operating power of the distribution system is composed of both active power and reactive power. Active could be called the working power and reactive is the non-working power. The active power does the useful work in driving the motor, whereas the reactive power just provides the magnetic field. Reactive power is the power that is consumed by reactive components such as inductive and capacitive loads to produce magnetic fields. Mostly, inductive loads utilize reactive power to create magnetic fields that rotates a motor. So we can conclude that the reactive power, its main aim is to provide the magnetic fields. So we don't really need this amount or big amount of reactive power, because the big amount of reactive power is going to reduce our power factor. So what we are looking for is to improve our power factor or to correct the power factor by minimizing the reactive power, as we will see how shortly. To know more about causes of low power factor, we have to understand the types of loads and their effect on the power factor. While most loads on electrical distribution system fall into one of the three categories, either resistive or inductive or capacitive. And in most cases or most appliances in our homes are commonly likely to be inductive. So what is the resistive load? It is any heating load that consume active or real power. It just consumes an active or productive power. And that is because its phase angle is zero. As we said before, that when the phase equals zero or the phase angle equals zero, this means a cosine of zero, this means a power factor of 1. And examples of these resistive loads are incandescent lights, toasters, water heaters, ovens, coffee makers, and etc. The second type is the inductive loads. We commonly use these loads in our homes. They utilize reactive power to create magnetic field that rotates a motor, and also it uses an active power. So the reactive power or the inductive loads cause the power factor to lag or cause a lagging power factor, as we will see how in a moment when we look at the waveforms of these loads. So these inductive loads require two kinds of power to operate. First, the active power, and second is the reactive power. Examples of these inductive loads are inductive motors, VFDs, or what is known as variable frequency drivers, vacuum cleaners, washing machines, air conditioners, and etc. The third and last type of loads is the capacitive loads. They are loads that don't exist in standalone format like resistive lights or inductive motors, and they have a leading power factor. Examples of this are the capacitors, capacitor banks, motor starting capacitors, and generators. Let's now look into these types of loads waveforms and compare the differences. First waveform here shows the resistive load. It is clearly evident that the current and voltage are in phase. So if you look at, for example, the voltage waveform here and the current waveform, we find that these two waveforms reaches their peak at the same time. So there is no out of phase angle. Whereas in inductive load, we can observe that the current lags the voltage. And when we say lags the voltage, we mean that the current reaches its peak after the voltage reaches its peak. So this causes an out of phase angle, which also causes a reduction in the power factor. Same thing happens in capacitive loads. We have a waveform that leads the other. We have here that the current leads the voltage waveform. And we mean by leading power factor here, we mean that the current reaches its peak before the voltage reaches its peak, which causes also a reduction in the power factor. Now, if we multiply the wave of voltage and the wave of current, we will get the power, and that is because power equals V times I. Now, if we want to observe what is the power for a pure resistive load, we will find that it is all in the positive side, or it's just an active power. So since the waveform is only on the positive side, so this means that we have a pure active power, a real productive power. Whereas in the pure inductance load, we find that the waveform goes into the negative side first, then the positive, negative and positive. And this means that we don't have 100% active power. This power in the negative side indicates the reactive power or the unneeded power, which in most cases goes back to the source. So for inductive loads, we just have half of the waveform, it could be more than half, also active power, and there is also some reactive power. Same thing happens with capacitive loads. When we multiply these two waveforms together, we get this power waveform, which also indicates half of the waveform is in the positive side, or there is a portion of this waveform in the positive side, and also we have a negative waveform. So our waveform goes from positive to negative, which means that we have in the positive side an active power, and in the negative side we have a reactive power or wasted power. So our aim when we say that we want to correct the power factor is to minimize this negative waveform over here as much as possible to reach unity, or to reach, for example, 0.95, 0.96, as much as we can, we try to improve our power factor so we minimize this amount of negative reactive power. Now, we can conclude that what causes a low power factor, of course, the inductive load or inductive loads in the first place. Then variations in power system loading can also cause a low power factor, and this is because the load on the power system is not always constant. It varies during the entire day, and this variation can cause a low power factor. And third, harmonic currents that are caused by computer devices can also cause a low power factor. What are the disadvantages of low power factor? With low power factor, we may select a higher rating of electrical equipments. For example, we may use a higher kVA rating of transformer, and this is because we are having a low power factor. Low power factor also can have an effect on transmission lines by selecting bigger conductor sizes or cable sizes, which will cost us more money. Also, large copper losses and poor efficiency can be a result of a low power factor, especially in transformers. And high voltage drops also can be one of the disadvantages of low power factor. And finally, a penalty from the electrical utility can be charged if the power factor of a 0.9 is not achieved in most countries. Now, when we say a power factor correction, what we really mean? To correct a power factor, we have to use a capacitor. These capacitors are rated in the unit kVAR, which is also the unit for a reactive power. So since we are correcting a reactive power, then we are going to use the kVAR. The amount of power capacitor required to correct a system to a desired power factor level is the difference between the amount of reactive power in the uncorrected system and the amount of the desired reactive power in the corrected system. We will understand this as a formula when we solve the example of selecting a suitable capacitor. We have two ways to install capacitors, either at each load or we can install at the main panel or the main distribution board panel. We can just install there a capacitor bank panel. And we already mentioned that most countries has a minimum target power factor of 0.9. If this 0.9 power factor is not achieved in our project, for example, utility is entitled to charge you a penalty. Important formulas. So in order to size a capacitor bank, we should know these formulas because we are going to use them while calculating and sizing the capacitor bank. First, the active power formula, which equals the apparent power into the power factor, and then reactive power, which is the root of apparent power squared minus true power, or the active power squared will give us a reactive power, and the apparent power, which equals the root of active power squared plus the reactive power squared. And finally, the power factor, which we already know that it equals active power over the apparent power. Let's see how these formulas are going to work in the example, but before we get into the example, let's conclude the steps of sizing a capacitor bank in 5 steps. First, to calculate the apparent power of the unimproved power factor. Second is to calculate the reactive power of the unimproved power factor. Third is to calculate the apparent power of the target power factor or the corrected power factor. And fourth is to calculate the reactive power of the corrected power factor. And finally, to size or to get the final size of the capacitor bank or the capacitors, we are going to subtract the unimproved reactive power with the target reactive power. We will see this in details when solving this example. Now, the example says that we have a project that has a transformer of 500 kVA that is operating at 480 kVA at 480 volts. So we have a present power factor of 0.75 or 75%. So the actual working power is 360 kilowatts. So we are looking for this main demand load. This main demand load is an important value that we are going to solve our equations based on this power. It is desired to increase the production to a power factor of 95. So we are asked here to improve the power factor from 0.75 to 0.95 and to clearly indicate the amount of improved active power after correction of the power factor. As we said, we have 5 steps to size a capacitor bank. First, we are going to calculate the apparent power of the uncorrected power factor, which equals the active power over the power factor, the 360 kilowatts divided by the 0.75, the present power factor, which will give us a 480 kilovolt ampere. Second is to calculate the reactive power of the uncorrected power factor, which equals the root of the apparent power squared minus the active power squared, which will give us a 317 kVAR. Third, we are going to calculate the apparent power, but this time is for the corrected power factor, which is 95% or 0.95, and we will get a value of 379 kVA. Then we will calculate the reactive power of the target power factor by taking the root again. We are using actually the same formula here and there, root of the apparent power minus active power squared, which will give us 118 kVAR, but this value is for the corrected power factor. Now to get the capacitor size, we said that we are going to take the difference between this amount, or the reactive power of the uncorrected power factor, minus the reactive power of the target power factor, which will give us at the end 199 kVAR. So this amount of a capacitor is sufficient to improve our power factor from 0.75 to 0.95. Then when we select a capacitor size, we will go for the nearest size or available size, which could be of 200 kVAR size of a capacitor or 250 kVAR. We were asked also to indicate the amount of active power improved in this system. So we can use this formula, which equals kilowatt, the root of the apparent power squared minus the reactive power squared, or this reactive power of the improved power factor, which will give us 465. Now let's understand what happened exactly using the power triangle. First triangle here shows the present power factor and its effect on the active load and the reactive load. So we are having an active load of 360 kilowatts and a reactive load of 317. So when we corrected the power factor to 0.95, we actually minimized this angle. And as mentioned before, minimizing this angle means also minimizing the reactive power. So we can notice here that there is a significant change of the reactive power from 317 to 118, which is 199 difference. Also, we can observe that the active power improved from 360 kilowatts to 465 kilowatts. And this means that 105 kilowatt improvement by improving the power factor from 0.75 to 0.95, which means now our system is more productive and has less drawbacks. Let's now have a look at a real capacitor bank panel. We notice that the capacitors are installed at the bottom of the panel, and there are also a number of contactors installed, and there is a power factor regulator installed at the door of the panel for setting the target power factor. So how the capacitor bank panel works? Briefly, the main idea is that we will set the target power factor using the power factor regulator as a first step. And this is how the regulator looks like. So we will set a power factor correction, for example, from 0.8 to 0.95. Then according to the demand load in our system, these capacitors are going to work. This means that it's not necessary that all these capacitors should work at once. They actually work in a technique called steps. And this is because the demand load varies during the entire day. So for example, if the demand load is at 50%, then contactors will close for half numbers of these capacitors, and the rest will stay on standby. So we can assume that half number of these capacitors will actually work to correct the power factor, and the rest of the capacitors will be on standby. If the demand load increases and power factor went below the target, then the contactors will take another step and close for the standby capacitors and connect these capacitors to the line to correct the target power factor or to reach the desired target power factor. This is the main idea behind how a capacitor bank panel works. Now, let's see what are the advantages of improving a power factor. First, it reduces electricity charges. Second, it lowers the amount of pollution resulting from releasing carbon emissions to the atmosphere. Third, it lowers heat generation in cables, switchgear, transformers, and alternators. And finally, voltage drop is reduced with a better or a corrected power factor. This is all about the topic of correcting a power factor. I hope that this topic was easy and it's understood by now. In the meantime, we should be able to size a capacitor bank panel easily.